Welcome to lecture 13. We are studying basic electrical engineering. We are studying loop analysis, and today we will solve a problem where we have to apply the super mesh technique. It's a technique that we need to use when we have a current source shared between two loops. The condition is this. Here we have a current source between two loops. Let's call it loop number 1 and this as loop number 2. So we have this current source, 2 milliampere current source shared between loop 1 and loop 2. In our earlier lecture, we have studied that if a current source is present in a loop, we don't write KVL equation for that. We just write the current of that loop equal to the magnitude of the current source present. But here we have this current source present in both loops. So if we consider this as a loop, we'll write I1 is equal to minus 2 milliamperes and I2 is equal to 2 milliamperes, which won't be correct. So how to find another independent loop and to avoid this 2 milliampere current source for loop number 2? We have to go for this path. This is a bigger loop bypassing this 2 milliampere current source and containing 6K resistor, 12 volt source and this 4K resistor. Now for loop number 1 we don't have to write an equation. I1 can be written as minus 2 milliampere straight away. Why minus? Because our assumed direction of current is clockwise and this 2 milliampere current source supplies a current that flows counterclockwise. So directions are not the same, therefore we put a minus here. Then let's go for the second loop, the bigger loop. Through this 6K resistor, there are two currents flowing, I1 and the current of this bigger loop. Let's call it I2. Since both the currents are moving upwards, they are in the same direction. Therefore, the net current would be I1 plus I2. And according to Ohm's law, the net current times the resistance gives us the voltage drop across the 6K resistor. Minus 12, because it's a voltage rise, the current enters from the negative side. Then this 4K, and there is only one current flowing through this resistor 4K, which is I2 is equal to 0. This is the KVL equation for the second and the bigger loop. Now we have two equations. I1 is minus 2 milliampere. We can put this value here. This becomes, but before we put this value, let's collect the coefficients, like coefficients together. This is 6K I1, 6K I2 plus 4K I2, 10K I2 is equal to 10. Multiple on the side becomes plus 12. Now we can put the value of I1 here. Putting this value minus 2 milli here. This becomes 6 times 2 minus 12. Kilo multiplied by milli is a 1. So this becomes minus 12. Minus 12 taken on the other side becomes plus 12. Adds in this plus 12 and becomes 24. So we have 10K I2 is equal to 24, or I2 over 10K. So 12 over 5. 1 over K is milliamperes. So we have I2 computed as 12 over 5 milliamperes. Since we are asked to find voltage drop across this 4K resistor, and there is only one current I2 flowing through this 4K resistor, and it causes a voltage drop with the same polarity as it is desired. So V out is, according to Ohm's law, the value of the resistor times the current flowing I2 12 over 5 milli. This is 48 over 5 volts. Right. There is one other unknown that we are required to find. We'll find the voltage drop across this 2 milliampere current source. In order to find this voltage drop, the voltage drop, let's call it V out 2. The voltage drop across this 2 milliampere current source. In order to find this voltage drop, we have to write KVL equation once again. 6K I1 plus I2, the voltage drop across 6K resistor, minus 12 voltage rise into 12 volt source, plus this voltage, because the current enters from the positive side, so voltage drop V naught is equal to 0. We know the values of I1 and I2, and we can find V out 2. Putting these values, 6K I1 is 2 milli plus I2, you have calculated to be 12 over 5 milli minus 12 plus V out 2. So we have only one equation, one variable. So V out 2 comes out to be minus 72 over 5 volts. That's all for this lecture. In the next lecture, we will study some more circuit analysis techniques. Thank you.